2, 1. Howdy, howdy, this is Mr. Potter. We're going to be starting a new course on pre-calculus, understanding the math that we need in order to be successful in our calculus course. And we're going to start by talking about functions and functional notation. But before we get into that, I really need to get into the concept of what a relation is. So a relation is a set of ordered pairs. In other words, I'm going to be taking a collection of ordered pairs. I'm going to be putting these curly braces. Now, we talk about set, we can use the word collection, we can talk about any type of group of ordered pairs, but they're going to come in pairs. So the number 1 is going to come with 3, for example. Or I could have a 2 coming with the 6. 3 may pair with the 13. And then I could have 4 comma 13. And I'm just making these numbers up right here. And then I could have a 4 matching with a 17 and 4 matching with a 3. So I've got a collection of ordered pairs, and this is a relation. And so what's important for us is that we'll often be talking about these different numbers in the ordered pair. So I may talk about the 1 or the 2 or the 3 or the 4 as being one set. And that set is going to be called the domain. And I may talk about this 3 or this 6 or this 13 or this 17 as another set. And this set is called the range. And so we have a set that's the domain. These are the first numbers that show up in our ordered pair. And we have another set called the range, and this is the second number in our ordered pair. Each ordered pair can be thought of as a relationship from the domain to the range. So this 1 comma 3 means that the 1 in the domain corresponds to the 3 in the range. The 2 comma 6 ordered pair means that the 2 corresponds with the 6. The 3 13 means the 3 corresponds with the 13. And the 4 also corresponds with the 13. That's what this pair right here means. It's okay for two numbers in our domain to correspond to the same number in our range. Similarly, just like 1 goes with 3 and 4 goes with 3, we could also have a number that goes to two different values and two different numbers matching to the same number. So it's okay for numbers to pair up or match up or duplicate in our domain and in our range when we're talking about a relation. And when we talk about a set like this with our domain and our relations, when we talk about our domain and we talk about a range, we often talk about mappings. And so a relation maps one set called the domain to another set called the range. And when we're looking at numbers like 1 and 2 and 3 and 4, there's lots of things that we'll use to talk about this. We'll talk about this being our domain, but we'll also talk about these being independent variables. And we'll use letters like T or X or I to represent these independent variables. And similarly, when we have our range, like our 3, our 6, our 13, and our 17, we'll have our range, but we'll also call these dependent variables. And we'll use letters like Y or some other letters to represent this, usually capital letters like C or R, if we're talking about cost or revenue. And when we're trying to talk about this relationship, this relation that maps, the 1 goes with the 3. The 2 went with the 6. The 3 went with the 13. The 4 also went with the 13. We'll call this a mapping. And we'll often use letters like F or G or other letters like that to represent this. And of course, if you've been in an algebra class before, you've seen letters like this before, where we talk about f, and we talk about g, and we talk about x, and we talk about y. We see these a lot in our algebra classes, but it's important to make the distinction between which are values, independent variables and dependent variables, and which ones are mappings, or as we often come to call them, functions. So what's important for us to understand here is that a function is a relation such that no element in the domain maps to more than one element in the range. So in other words, when I'm talking about the relationship that we had before, the relation 1, 3, and 2, 6, and 3, 13, and 4, 13. The problem is when I came up with this 4, 17, this is actually a problem because I've got one element in my domain that maps to more than one element in my range. In other words, if my independent variable repeats, then my dependent variable has to be the same. It can't be different. So this is not a relationship. But here's an example of a function. So let's say I have this function. I've got 1, 3, 2, 6, 3, 6, 4, 6, 5, 9, and 6, 9. Now you notice that there is some repetition, and that's acceptable. Our dependent variables can repeat. The only thing we have to watch out for is our independent variables may not have multiple range values. And notice that each of these numbers, 1, 2, 3, 4, 5, 6, they don't repeat. If they did repeat, then I'd have to make sure that the corresponding dependent variable also repeated. Now in these cases where the 6 repeats, that's okay because my independent variables are different. If I were to look at this as a mapping, my domain would have 1, 2, 3, 4, 5, and 6 in it. That would be my domain. My range would have 3, 6, and 9 in it. And the actual mapping would be 1 goes to 3, 2 goes to 6, 3 also goes to 6, 4 also goes to 6, and then 5 goes to 9, and 6 goes to 9. Notice that every element of my domain has one target that it hits in the range. That's really the essence of having a function. And this mapping, in other words, this correspondence between my independent variable and my dependent variable, between my range and my domain, that mapping is called a function. So, we're going to talk a little bit more about functional notation. We're used to seeing, in our algebra classes, we're used to seeing something like y equals a function of x, where x is our independent variable, y is our dependent variable, and f is our function. And sometimes, we actually write this out as y is a function of x. And if we're really lazy, sometimes we'll just write it as y parentheses x. Now, all of these mean the same thing. They all mean that X is our independent variable, Y is our dependent variable, and there is some function that connects them. So we're always going to say Y is a function of X. That makes it clear that 1, we have an independent variable, it's X. 2, we have a dependent variable, that's Y. And 3, it is a function, which means it matches that definition we talked about, where each element in our domain maps to only one distinct element in our range. So you might see f of x being another way of writing that. In this case, it's clear what my function is. It's clear what my independent variable is. It's just not necessarily clear what my range is. But we actually get into that when we start talking about how we can represent these. And we represent these functions often using the rule of 4. Because there's really 4 different ways to represent functions. There are 4 main ways. So one of the ways that we can represent a function is tabularly. In other words, I have a table with x's and y's, 1, 2, 3, and 3, 6, and 9. This would be an example of a table. I may also see something graphical. So graphical, where I will have an x-axis, a y-axis, and I can talk about points on my graph. So this would be a set of ordered pairs where no one x value has multiple y values. I may also see it verbal. In other words, a wordy description of what the function is doing. So I may see something like the y value of a function is 5 times the x value. And this actually describes a function. And the one that we're probably the most familiar with is algebraic. So we might see something like y equals 4x plus 3 for x in the set 1, 2, 3. Now notice that I can take any of these and I could describe it verbally. The y value is 4 times the x value plus 3. Or I could graph each of those points and come up with a graphical description. Or I could take this equation and make a table out of it. As a matter of fact, any of these I can do. And that's one of the power of the rule of 4, is that we can actually represent it not just with that 1 out of the 4, but we can take any function and represent it in any of those 4 ways. What we're really interested in this class, though, is coming up and solving problems using functions. So I've got a function here. I want to evaluate f of x equals x squared plus 2x for the following value. So I'm going to start off by saying x equals 3. Then I'm going to say let x equal some variable a. And I want to do it a third time, and I want to say let x equal the expression 2h minus 1. Now all of these use substitution. In other words, everywhere we see an x, we're going to replace it with some particular value or expression. So in the first case, I want to evaluate when x equals 3, so I'm really looking for f of 3. And the way I do that is everywhere I see an x, I'm going to replace it with 3. So this is going to be 3 squared plus 2 times 3, or 9 plus 6, which gives me 15. If I want to do b, I'm going to have to evaluate f at the variable a, which means everywhere I see an x, I'm going to replace it with a. So a squared plus 2a. And those are not like terms, so that's as simplified as I can get. And for c, I want to replace every occurrence of x with this expression 2h minus 1. So f of 2h minus 1 is going to be the expression 2h minus 1 squared plus 2h minus 1. And I'm going to expand this binomial, so that's going to be 2h minus 1 times 2h minus 1, which gives me 4h squared minus 4h plus 1 plus 2h minus 1. And then I'm going to want to combine my like terms. I've got negative 4h and positive 2h. So I'm going to get 4h squared minus 2h, and the plus 1 and the minus 1 make a zero pair. They're going to eliminate each other. So this expression is the result of evaluating this function for the expression 2h minus 1. Notice that when we're evaluating a function, we can get a numerical answer or we can get an algebraic expression. So just be aware of that. Another type of problem that we can see involving functions says that given g of t equals 2t squared minus 3t, find where g of t equals 2. And in this case, we are going to have to solve. So we're going to have 2t squared minus 3t equals 2. And I'm going to have to solve this algebraic expression. So I've got 2t squared minus 3t minus 2 equals 0. In general, when we're solving quadratic equations, it's often best to actually get it equal to 0. And there's two ways that we can do this. One way is we can try and factor this out. Notice that 2 times negative 2 gives me negative 4, and I know that a negative 4 plus 1 will give me this negative 3. So I could rewrite that middle term, minus 4t plus 3t, plus 1t. Let me erase that. Plus 1t minus 2 equals 0. And then I can factor by grouping this expression and this expression. So in this case, I would have 2t times t minus 2 plus 1 times t minus 2. And that would give me 2t minus 1, 2t plus 1 times t minus 2, which would give me 0. And by the zero product property, I know that 2t plus 1 equals 0, or t minus 2 equals 0, which gives me a solution t equals negative 1/2, or t equals 2. And that's one way I could solve it. I could also just go through with the quadratic formula. I can know that my function is going to be equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So I would have 3 plus or minus the square root of 9. This is going to be 4 plus 8, 16. So plus 16 over 4. So this is really 3 plus or minus the square root of 25 is 5 over 4. And if I were to add 3 plus 5 is 8, 8 divided by 4, that tells me that t equals 2. If I subtract 3 minus 5 is negative 2, and negative 2 divided by 4 is negative 1/2. So I get the same solutions either way. What's going to be important is to take these solutions and actually check them. In other words, when I take 2 times 2 squared minus 3 times 2, do I get 2? Well, that's 2, 4, 8. 8 minus 6 is 2. Yes, we do. If I take 2 times negative 1/2 squared minus 3 times negative 1/2, do we get 2? Well, this is 1/4. That's 1/2. And if I take 1/2 and add 3 halves, that's going to give me 4 halves, which is 2. So I can check my answers to make sure that they do satisfy the original expression we were trying to solve. So that's another thing that we can do. I can also take an algebraic expression, an equation, and solve for it as one variable in terms of the other. In other words, here I'm trying to solve for m, trying to get m minus itself. So if I have 3m plus 2n equals 12, I want to get m by itself, so I want to get rid of this addend. So I'm going to subtract 2n from both sides. That's going to give me 3m equals 12 minus 2n. And then I want to get rid of this 3, so I'm going to divide every term by 3. And so I get m equals 4 minus 2/3 n. So I should be able to take any algebraic expression and try and solve for one variable in terms of the other. Now, notice that this is an easy one to solve because both of these coefficients, both of these variable terms are linear variable terms. But remember that in Algebra 2, we often had things like circles. And it's going to be hard to find y as a function of x or x as a function of y. Let me erase that. It's going to be hard to find y as a function of x or x as a function of y because it's hard to deal with those quadratic terms. It's hard to deal with those squares. Let's do another one. Let's say I'm given this table. I want to find q of 3. So if I'm finding q of 3, I want to know, basically I'm asked to find y when x equals 3. And I can look at the table and say, okay, when x equals 3, y ends up being 8. So I could say that q of 3 equals 8. And I can work backwards as long as I'm aware of those things. Notice here I'm saying find q of p equals 8. Well, here's an 8, and here's an 8, and here's an 8. So if I say q is equal to 8, so in other words, I'm trying to find p when q equals 8, well, p equals 3 satisfies it, p equals 4 satisfies it, and p equals 6 satisfies it. And we're aware from Algebra 2 that we can have multiple solutions to an equation. It's okay to have, 2 solutions to a quadratic equation. It's okay to have 3 solutions for a cubic equation. When we're dealing with this tabular data, though, it's possible to have multiple solutions. So just be aware of that. The last example, the last rule of 4 that we really haven't talked about is graphing. So I've got an example. Given the graph of y equals c of x, I want to find c of 1. If I'm trying to find c of 1, then what I'm doing is I'm actually going to find out, okay, when x is 1, I want to find y when x equals 1. So when x is equal to 1, that's this value right here, because we're counting by units on this graph. Then I want to know what happens at y. So if x equals 1, that's going up 1 unit, up 2 units. So this is the point 1, 2 on the graph. So we could say y equals 2 when x equals 1. Now similarly, I could have this same situation, and instead of finding out where c equals 1, I could find x when c of x equals 2. And if c of x equals 2, well, that happens here, but it also happens over here. Notice that when y equals 2, x can have multiple values. So here x equals 1, or x equals -3. And neither one of those are a more important solution, so neither one of those have to go first. The order really doesn't matter. What's important to understand from today's lesson is that we're talking about the rule of 4. We're talking about how to solve equations verbally, algebraically, tabularly, and graphically. And we're also making the distinction between a relation and a function. Remember that a relation means that each independent variable is going to match up with at most one dependent variable. And just because you're a function one way doesn't mean you're going to be a function the other way. For example, in this one. Here, if y equals 2, there's only 2 solutions for x. But if x is 1, there's only going to be 1 solution for y. So it's important to understand the relationship between relations and functions. when a function is a relation, when a relation is a function. Those are important key points to make. So once again, this is Mr. Potter. Thank you for watching. Have a great day.